speaker is Mariusz Mirek from the University of Wrocław. The title is The Multilinear Circle Method and its Consequences in Pointwise Ergodic Theory.
Okay, thank you very much.
Yours.
I'm really happy I can give this talk here in Warsaw. And so I will talk about some hopefully interesting problem arising in classical ergodic theory. And so let me start. So I will, the first part will be very elementary, just to motivate the problem. So we will be, because we will talk about pointwise convergence problems for a second. Ergodic averaging operators, mostly we will be interested in integer shift system, so which is the set of integers with sigma algebra of all subsets of integers in the counting measure, and shift operator that takes integer x and sends it to x plus 1 or x minus 1 depending on the context. But so let's think that this is this kind of shift. So presumably from the dynamical point of view, so this integer shift system is not very interesting. This is sigma finite integer system, but it's very important, and we will see this from the point of view of pointwise convergence problems.
What is this P of set?
This is the subset of all sigma algebra of all subset of integers. And so here we have, I listed just add some number of other interesting systems, the circle rotation, just to give a feeling what we will discuss about. The torus with the Lebesgue sigma algebra, the Lebesgue measure, and the rotation about irrational angle on the torus. So we add just irrational angle to x, and we consider this modulo 1. And this is important from the point of view of equidistribution problems in ergodic theory or number theory. So here we have another interesting system, circle doubling system, which is again torus with Lebesgue sigma algebra, Lebesgue measure, and multiplication by 2 modulo 1. And finally we have continued fraction system. So this is some Gauss measure, Lebesgue measure with this density, everything normalized to have mass 1, and the continued fraction map, this is 1 over x modulo 1. So therefore the nth iteration of this gives us the nth digit in the continued fraction expansion of the number x. Okay, so and now here let me just formulate Bergelson's question from early 1990s, and he was interested in L2 norm convergence, and as well as pointwise almost everywhere for this kind of complicated multilinear averages. So we will consider here a fixed number k, a probability measure space. From now we can think that we work with a probabilistic measure preserving system, and this probability space will be equipped with a certain family of invertible commuting measure preserving transformations, which acts on x and takes values z. And then we also fix polynomials with integer coefficients, and the multilinear polynomial ergodic average is defined in this way. It's the average of the products where the orbits are taken along this polynomials with integer coefficients. And the question is whether they converge in L2 norm in the sense of the Hilbert space, or pointwise almost everywhere as n goes to infinity. And so, so in a moment I will tell you what is known about this problem and what is unknown. And so, but before we do this, I would like to motivate this problem and show you how it arises in ergodic theory and why this kind of multilinear or multiple ergodic averages are important. And sometimes we will abbreviate, I will call this average, so we will talk about single transformation case whether all, whenever all transformations here are equal to each other. So when we have whenever this condition holds. Okay, but before we do this, let's start with the classical case. So the classical ergodic average, so it has this form. So this is the Berkeley von Neumann average, and we know that this object is very useful when we study recurrent points, because if we test this on the characteristic function of a measurable set, then we see that this quantity, this is precisely the mean value of the number of visits of this orbit in the set X, in the set E, sorry. So that's the, so this is, in other words, it counts how many times the orbit returns to the set E. And so, and if we are able to find norm or pointwise limit for this, then we can deduce, for instance, the Poincaré recurrence theorem, which says that if we work with a finite, or let's say probability measure preserving existence with a measurable set which has positive measure, then the measure of this event is positive for some integer, in fact for infinitely many integers. So this is Poincaré, it's a version of, so this is a way to formulate Poincaré recurrence theory. In other words, it says that the orbit returns to infinitely many often. And so in the early 1930s, von Neumann established norm convergence for this, and for this ergodic averaging operators. He showed that this ergodic averaging operator converges in L2 norm to the projection of all functions on L2 which are T invariant, so T invariant, which means that ft of x is equal f of x, and then this was extended by Berkhoff to the situation of pointwise almost everywhere convergence, where we take function in LP whenever p is between 1 and infinity, excluding the infinity endpoint, and then we can show that the limit exists in the sense that it converges pointwise almost everywhere for a certain function f star, which also belongs to LP. So that was the beginning of this story of investigation, those kind of averaging operators. But then in the early 1980s, Bourgain started to study more general averaging operators along polynomial orbits. And the reason why Bourgain started to study pointwise almost everywhere convergence for this was twofold. First, so it was motivated by a question of Alessandra Bello and Hilary Furstenberg. And so Furstenberg was motivated by certain result from additive number theory or additive combinatorics. This is the result of Sarkozy, which says that if we have a subset which has positive upper density, so which means that, so we say that a subset of integers has positive upper banach density if this lim sup this n goes to infinity of this quantity, if this is positive. So then we say that the subset of integers has positive upper density. So under this assumption, so in other words, we think that this set is fairly large inside the set of integers. And then, so under this statistical assumption, Sarkozy showed that in subset of integers with this property, we can always find two integers whose difference is a perfect square. So in other words, we can always find x and n with this property that x and x plus n squared are elements of a set in question. So, and Furstenberg was motivated by trying to understand this phenomena from the point of view of ergodic methods. And so he, in fact, established norm convergence for this operator, and then he showed that whenever p is an integer with, whenever p is a polynomial with integer coefficient, then the extension of polynomial Poincaré recurrence theorem holds. So we have that for every set with which has positive measure, for every subset which is measurable with positive measure, then the extension of Poincaré recurrence theorem holds. So this even has positive measure for infinitely many integers. So that was motivation of Furstenberg to study this. In a moment, I try to explain how this, and in other words, from this, we can immediately deduce that subset of integers with positive upper density have this property that we can find two integers x and y whose difference is precisely equal to this polynomial. So I'll try to explain this in a moment. So that was motivation of Furstenberg to study this kind of averaging operators. And Alessandra Bello, she was interested in pointwise convergence for this because she wanted to understand equidistribution problems, and in fact extension of Weil equidistribution problem. We know that Weil at the beginning of 20th century, he proved that if we have a polynomial which has at least one irrational coefficient, then the fractional parts of this polynomial are equidistributed in the unit interval. And so in the equidistribution, so we have this. So in other words, the equidistribution, this is a certain statistical statement that, so we can say that the sequence an is equidistributed whenever an belongs to this, and we divide by n, so this is equal to b minus a. Okay, so then we say that if this holds for every real numbers between 0 and 1, then we say that this sequence an is equidistributed modulo 1. And Bello, so in particular, we know that the fractional parts of P of m are equidistributed whenever P of n is a polynomial which has at least one irrational coefficient. And Bello, she asked whether this can be extended to the situation where these sets here are replaced by Lebesgue measurable sets, and whether this now can be replaced by the Lebesgue measure. But then we have to start presumably from this and ask about this question almost everywhere. And then she immediately end up with this kind of averaging operators here for whenever t is a rotation about irrational angle, essentially. So this is what how this question arises in equidistribution theorem, and then pointwise almost everywhere convergence. This is precisely what we are looking for to recover this statement. And so then Bourgain started to study this problem, and he invented a very robust tool to study this kind of ergodic operators with polynomial orbits. The methods come from analytic number theory, and in fact the key thing is a classical circle method of Hardy-Littwood, which was used to count the number of solutions in the Warring problem, which asserts that every integer can be represented as a certain number of squares of kth powers, depending on. And so Hardy-Littwood, and in fact Ramanujan was also involved. They figure out how to do this, and this kind of methods turn out to be essential to ask this question. So at this moment, this is very far, but I try to at least today give you an idea how these methods come up in the proof. And now, so let me tell you now, because so far we touched the linear ergodic averaging operators, and now let's try to understand why multilinear. And so Furstenberg in 1977, he proved the following extension of the Poincaré recurrence theorem. It's called the multiple recurrence theorem of Furstenberg. If we have this measure preserving system on a probability space, and we consider measurable set with positive measure, then for every integer, this lim inf of this averaging operator is always positive. And in particular, this implies that for infinitely many integers, the measure of this event is positive. So therefore, we see that if we restrict ourselves to k equal 1 here, then we immediately recover the Poincaré recurrence theorem. So therefore, this is extension. So here we have more intersections, so therefore we get smaller and smaller set, and that's it's difficult to show that the measure of this event is positive. But yeah, Furstenberg, he was able to show that for arbitrary k, we have this. The measure of this event is positive infinity of. And now, so let's try to understand. Here is a remark how this leads to problem about understanding of averaging operators and the limiting behavior. Because here we see that if we take a look at this average, then we immediately see, so this is the scalar product with the multilinear averaging operator, which has this form: single transformation, and orbits are taken along multiples of n, 2n, 3n, kn, and so on. So therefore, now we see that if we understand, this is much weaker statement, but if we understand the L2 limiting behavior, then we immediately be able to show that this limit exists here, and then we will have to work to show that it's positive, which is not obvious, but under certain circumstances, we are able to show that this is positive, and even here in this generality. Okay, but now, so this remark shows the relation, how this kind of things to study these operators. And now, so the original motivation of Furstenberg was to understand this famous theorem of Semeredi, which says that if we have subset of integers with positive upper density, so which means that this holds, then for every integer there exists infinitely many arithmetic progressions in A of length here k plus 1. Okay, so in other words, we can find the patterns of this form in A. So this is very interesting phenomena in this additive number theory or additive combinatorics, because here so this assumption is purely statistical. It says nothing about the structure of the underlying set, but on the other hand, it says that if this set, so this is a certain quantity that measures largeness. So every subsets which have this property that they have upper density, we can think that they are large in the set of integers. And then, so assuming this, we can deduce that our subset inherits certain arithmetic structure in the sense of the existence of these patterns, in the sense of the existence of arithmetic progressions. And now, so Furstenberg, he had some ingenious insight about this problem, and he realized that existence of arithmetic progressions, this is a problem about recurrence of orbits so in other words, he understood that this problem can be interpreted as a recurrence problem in ergodic theory. And so therefore, he first proved this extension of Poincare recurrence theorem to these multiple events. And then he showed a certain principle which these days in the literature is called Furstenberg correspondence principle, and it says that if we have, and this is a certain bridge between this arithmetic problems and problems in ergodic theory, which immediately reduces arithmetic problems to problems in ergodic theory. And so here is the statement. If we have a subset of integers which has positive upper density, then we can find a probability measure system and a measurable set in this system with the property that the measure of this set will be precisely the density of the set A. So therefore, this set is measurable and has positive measure because density is positive. And then, invoking the results from the previous slide, Furstenberg theorem, which is a statement, which is extension of Poincare recurrence theorem, for every subset which has positive measure, we have that the measure of this event is positive. So therefore, we know that this event is positive by the previous theorem. And the second part of the correspondence principle says that the measure of this event is dominated by the density of this set. And now we can immediately see, as here, this is the shift operator on the set of integers. And now from this inequality, we see that this density in particular is positive. So therefore, if density is positive, then underlying set must be non-empty. And if this is non-empty, then this means that we can find certain element x with the property that x plus n, x plus 2n, and so on, x plus kn belongs to A. So therefore, this gives us immediately this existence of these patterns of this form in the set of integers. So that's how this. So two ingredients are important. If we ask about the question about these questions, if we ask about the existence of certain arithmetic progressions, or in a moment we'll see more complicated patterns, then we have to prove, we can immediately translate this into language in ergodic theory, and two ingredients are needed. Thus, and this is some kind of meta theorem, it works in a very, very general setting, and as I said, this is a certain bridge that connects this language from this world from additive combinatorics with the ergodic world. And then we have to prove recurrence theorem, and here usually this is a challenge to prove that this limit is positive. And therefore, but in order to show that this limit is positive, usually we can we can focus on this, but there are some situations that sometimes we immediately attack the existence of the limit, and we ask about the L2 norm convergence, just to show that the limit here exists, and then showing the fact that this is positive, it's a different story. And okay, and now, because I started from this question of Bergelson, and now I hope I can motivate how this ergodic polynomial, this multilinear polynomial ergodic averages arise. And here is the.
Excuse me. So I'm wondering if in this correspondence principle it's possible to replace these multipliers by polynomials, be one of them, be two of them.
Yeah. That
still holds.
Yes, it still holds, and even if you replace this by functions, which are increasing, then also you can deduce a similar statement. Yeah, it's very very robust, from this point. So therefore, this is why I said that this is some kind of meta theorem. It holds under very mild conditions. Okay, and here we have a beautiful result of Bergelson and Liebman from 1996, who showed a polynomial extension of the of Semerelli's theorem, and it says that now this patterns arithmetic progressions can be replaced by polynomial patterns. So in other words, here let me just mention this. Now we ask, so Semerelli says that we ask about arithmetic progressions x plus n, x plus 2n, and so on, x plus kn in subset which has positive upper density. And now the question is, what happens if we have given polynomials with integer coefficients, whether we can find configurations of this form. And yes, so this is what was shown by Bergelson and Liebman by using ergodic methods. If we consider polynomials which have integer coefficients, and for some technical reasons we assume that all these polynomials have zero constant term, then we can deduce this kind of extension of Poincaré recurrence theorem and Furstenberg recurrence theorem. And now So the difference is that now the orbits are taken along this given polynomials. And here even we can go even further, and instead of single transformation, we can consider multiple transformations. As long as they are invertible, they commute. And so this implies in particular that the measure of this event is positive for infinitely many integers. And now the difference, so here, this situation here corresponds to the case where all T1, T2, Tk are equal to one transformation. So this is one-dimensional situation. But if we allow to have here different transformations, then this corresponds to multidimensional situation, where we now, instead of set of integers, we consider vectors, and now we just take the corners. So therefore, if we take a look, so here, for instance, if we assume that our polynomial Pn, P1 is n, and P2 is n squared, then we may have a situation that we are looking for the, okay, so this, okay, for instance, this situation x, y, x plus n, y, x, y plus n squared, it corresponds to the situation like this. I will put here x, y, the origin, or maybe not, maybe, okay, so let's put here x, y here, and then, so here, this is x plus ny, and here we go n squared x, y plus n squared. Okay, so we take a look, this corresponds, to the configurations like this, that we look for the corners, and more general, induced by this polynomial. And again, the same story. Here we immediately see that this expression can be interpreted as a scalar product of this multilinear ergodic averaging operators, which is paired with this characteristic function of the set E. And that's why it's important now. This motivates, why we study this more general type of convergence in L2 or pointwise almost everywhere. And here, this is the slide that explains the current state of the art in the context of single transformation, where we have just one transformation, multiple averages, and general polynomials with integer coefficients, and and everything is defined on a probability measure preserving system. And so this story, the systematic studies of non-convergence started since Furstenberg. It was 1977, and the situation of the bilinear operator, we have just two factors here along linear orbits. It was established by Furstenberg. And so that was the beginning of this story. And then in the mid of 1980s, Bergelson started to study more general operators of this form with polynomial orbits. And he was able to establish limit under very specific assumptions for weakly mixing systems. So that was the first important paper that gave evidence that this problem of norm convergence, of the existence of the limit for polynomial configurations can be it may be promising. And then a very fundamental paper of Furstenberg and Weiss comes from 1996, where they established they handled two important cases. The first case, it was the existence of this parabolic configurations like this. And that was the paper where the concept of characteristic factors were seriously studied in the context of the existence of the limit for this kind of averaging operators. And they established the existence of norm convergence for this ergodic operators in the bilinear case when the first polynomial is linear, the other is quadratic. And in fact, they reduce the problem to the situation of to the trilinear situation when all orbits are linear, are taken along the multiples of n. And so this was these two results were discussed in the paper of Furstenberg and Weiss from 1996. That was a very important paper, but on the other hand, it showed that those two problems, this quadratic and trilinear, are very close to each other at some point, and that was some barrier to study the operators along polynomial orbits. And first, it was so the challenge. So from this paper, it follows that one has to start with linear orbits first. And in 2002, Hoss and Kra and independently Tammy Ziegler, they established non-convergence for arbitrary ergodic averaging operators along orbits which are multiples of n, which are linear. And that was this is very important, two important papers in this area where the phenomena of norm convergence was completely explained. And then Sasha Liebman in 2005, he proved norm convergence in this situation for arbitrary polynomials. So that's now here I would say that this situation is fairly well understood. The single transformation case, so where all transformations here are induced by the same measure preserving transformation. And the situation is completely different for pointwise convergence when we ask about the behavior of this limiting behavior of these averaging operators for almost every x. And in the early 1990s, Bourgain only proved pointwise almost everywhere convergence in the bilinear situation, in the situation of Furstenberg. And for k equal 2, we have two factors, and orbits are multiples of n. And since that time, there was not much done until recently. So we started with my collaborators, Ben Krause and Terry Tao, we started to study this problem first in the context of Furstenberg and Weiss. And the reason was there was some important development in additive combinatorics, and that was a trigger for us to start to study this problem. And so we were able a few years ago to show that this kind of ergodic averaging operators, whenever P of n is arbitrary polynomial with integer coefficient and degree bigger or equal to, they converge almost everywhere. So in other words, the Furstenberg-Weiss averaging operators converge almost everywhere, not only in L2 norm, but almost everywhere also. And so here, and this handles essentially the situation of single transformation, and even at that time, in this paper, we were unable to go beyond the bilinear situation. That was, the bilinear was also from many reasons, the best what we could do, and still breaking the barrier and going, to study more general multilinear averaging operator is a challenge. Here, I would like to mention a very important and very impressive results of Frantzikinatis and Kutza. Kutza now is Frantzikinatis is a professor in Crete, and Boris Kutza is and now he has a position at the Bergelson University. And so they proved a very impressive result. They established norm convergence for this more general situation, multilinear, and whenever here we allow orbits to run along, to be induced by different invertible commuting measure preserving transformations. So here, and they can prove, they were able to prove that whenever polynomials have integer coefficients and are linearly independent, so here it's very important, then the limit exists. So in other words, then the rational Kronecker factor is characteristic for this average. So therefore the limit exists. And in particular, if we assume that our transformations here are totally ergodic, which means that every power is ergodic, then these averages converge to the product of integrals. So therefore now the time average here converges to the space average, in the sense of the L2 norm convergence, the difference, the L2 norm of the difference converges to 0 as n goes to infinity. So this is a very important result in this in ergodic theory for this norm convergence of multilinear ergodic averages. And
did they use inversion of correspondence principle?
Yeah, they use the inverse. The inverse theorem. They are, things were reduced to study higher order Fourier analysis of Gauers and some development which was done by Peluse. It's a very impressive piece of work. Very, 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 very impressive. And here now, because we studied, so now we are familiar with the situation of single transformation and for these commuting transformations, but so I have to tell you that, so this is just only part of the story because the problem is formulated in a more general situation. So, in fact, now it's known as a conjecture of Furstenberg, Bergelson, Liebman, and it's defined for even for transformations which not necessarily commute. So if we consider now a nilpotent group of measure-preserving transformations in a probability space and consider polynomials with integer coefficients, and these TJs are taken from this group, are measure-preserving transformations from this group, then it's conjectured that the almost everywhere limit for this complicated multiple averages exists as n goes to infinity. And so what was very, very impressive in 2012, Miguel Walsh established norm convergence for this complicated ergodic averages. And so in other words, so he established this in the nilpotent setting by very, very clever application of Hahn-Banach theorem. The paper is very short, and it's a very beautiful application of Hahn-Banach theorem to show that the L2 limit for this averaging operators exists. And so, on the other hand, we can ask what happened, if we drop the assumption about the nilpotency. So, Bergelson and Liebman showed that if we drop this assumption, if we consider a group of measure-preserving transformations which is solvable but not nilpotent, then the even L2 convergence may fail in this situation. So therefore, presumably the nilpotent setting, this is the best what we can expect in this situation, but you know, in this generality, this problem is widely open. And even for linear transformations, in the situation when m is equal 1 here, even if we have the transformation, the average like this, then the situation is widely open except one case with my colleagues Alex Ionescu, Kosz and Tomasz Szarek.
Tomasz
Zachary, yes. That's a good point to emphasize that this is Tomasz Zachary. And so we established pointwise almost everywhere convergence in a very specific situation if we consider measure preserving system with transformations that are invertible, measure preserving, and satisfy these commutator relations. In other words, we can think that this transformation span certain nilpotent group of step 2. Then for every polynomials with integer coefficients, this kind of averaging operators converge almost everywhere for any function in LP space. So that's this is what is now possible, and now we are working on certain extension of this to more general groups, and then we can handle nilpotent groups of step 3 and 4. But yeah, we have appetite, to understand the general case, which is fairly complicated because of very complicated structure of 3 nilpotent groups, and they are given by certain complicated inductive. There's some inductive construction that leads to universal nilpotent groups, and we need to understand certain aspects. So now the problem that we want to understand is about understanding this underlying structure. This is a very combinatorial group theoretic problem that we encountered to push things further for more general groups. And but on the other hand, very, very exciting. So we are working on more general situation to extend this to general nilpotent groups. And finally, because so far we talk about in the context of pointwise convergence, we talk about only bilinear situation, but recently with Darek Kosz, Sarah Peluse and Jim Wright, we were able to break the barrier and establish something for multilinear averaging operators, and we in fact broke the barrier in 2 ways. The single transformation case. Now we can establish pointwise convergence for this general ergodic averaging operator, and now we can consider commuting transformation, which are distinct as long as they are invertible and commute, and general we may have here so this covers the multilinear situation. K can be arbitrary but fixed, and we can establish pointwise almost everywhere convergence here in this situation as long as our polynomials here that arise here are general but have distinct degrees. So therefore we can think here we have n squared and cubed and so on. For instance, this is the situation. So at this moment, the fact that distinct degrees is critical for the method that we have. And now if we combine our result with the results of Franzikinakis and Kutza, and we assume that the orbits are totally ergodic, then we see that this space multilinear average converges to the product of, this time ergodic averages converges to the product of space averages almost everywhere, as long as here we have polynomials with distinct degrees. So here our assumptions are stronger at this moment than the assumptions of Franceschiniakis and Kusa, because they were able to prove this L2 norm convergence for this under the assumption when the polynomials are linearly independent. But at this moment, for our method, it's important that we have polynomials with distinct degrees. But anyway, we were able to go beyond the bilinear operators and beyond the single transformation case. So this is what we have now. This is our knowledge about this asymptotic behavior of this averaging operator. But still, we are very, very far from this, what is predicted by this conjecture of Furstenberg, Bergelson, and Liebman. And and also, what is here surprising, that the fact that we work with polynomials with distinct degrees, because at the first glance, they are much more complicated than linear orbits. But this helps a lot to understand this problem. And now it seems that the challenge, I believe that at some point, the situation of polynomials which are linearly independent will be covered, and maybe even the method that we develop will be important. But the situation where here we have linear orbits, n, 2, and 3, and so on, this will be a very challenging situation, which is completely different from this what is provided by this by the case where we consider polynomial orbits. So that's very surprising, because at the first glance we would say, yes, the linear orbit should be simpler, but yeah, this is unfortunately different. Okay, so how much time do I have?
5 minutes.
5 minutes. Okay, so if I have 5 minutes, maybe I will skip, because I prepared some number of slides about the method of the proof, but maybe I skip that. But I will tell you just one thing. So what is why this is I have to find this slide. Yeah, okay, this. So here, one of a very important ingredient in the proof is certain structural theorem, which initially, in the single transformation case for polynomials with distinct degrees, was discovered by Sarah Peluse in a very deep paper, where she wanted to understand a problem of Gauer's. So she wanted to quantify a certain function, because when we consider the question of Semeredi, we can immediately ask, if we denote function r of n, if this function denotes the size of the largest subset of the first n integers which contain no configuration of this form, then we can ask, how large this function is. And so if all polynomials here are linear, then both Semeredi and Furstenberg implies only that this function behaves like little o of n. But Gowers, at some point, and this is how everything started and how the development of higher order Fourier analysis became so important because of Gowers, who wanted to understand the behavior of this function in the context of Semeredi theorem for arithmetic progressions. And he was able to quantify this and show that this behaves like n over log n certain power gamma n. And now we have significant improvements because of certain recent paper of Lang, Sah, and Sauni of this function. But what is important here, Gowers at some point posed a question: what happened if, in place of arithmetic progressions, in place of multiples of n here, we will consider general polynomials? And there was a question if this can be quantified, and this question was open for quite a long time until Sarah Peluse figured out how to do this in the context of polynomials which have distinct degrees, and she was able to show that this function, the upper bound, behaves like this by establishing certain structural theorem, which is the so-called inverse theorem in this higher order Fourier analysis. And it says that if the underlying average here is large, then we can show that each function here correlates with some other particular function which has a particular structure, in the sense that on the Fourier transform side, this function hj is supported in certain arcs, which are small neighborhoods of rationals with small denominators. And this is essentially what this notation says. And that's very important to prove something which is an extension of Weil inequality from equidistribution theory. So originally Weil proved some result about the behavior of exponential sums, where here this is E, this is this notation from number theory, E to pi I q of n, where q of n is this polynomial of this form. And he was able to show that if this is large, then the coefficients must also belong to certain arcs which are centered at the rationals with small denominators, smallness dictated by this scale. And here we were able to extend this result to prove some extension which has, first challenge was to figure out how to extend something which is purely number theoretic to this functional analytic language, but we were able to extend this inequality of Weil for exponential sums to this functional analytic language, and derive some inequality which has certain losses, especially in this scale n here is important, and provides some good tool to handle these problems, these pointwise convergence problems. But maybe I won't enter into details, because that would require much more, and I don't want to extend, so maybe I'll stop here. Thank you very much.
Thank you. Do you have questions?
What can you say about counterexamples? So you say that you have example of a solvable group for which the conjecture would not.
Yeah, these are, yes. Okay, I know that these counterexamples exist, and they are done for solvable groups which have exponential growth. The balls which are consider with respect to the word metric, they grow exponentially. And I think this is the class of groups where it's a good example where you can find this counterexamples. And yeah, as far as I know, these are some kind of groups which are similar to Lamplighter groups, which can be used to disprove this. And this shows that that the nilpotent situation is the best what we can expect here. Yeah.
But it's not something simply described group. It's
No. They are usually defined inductively as far as I remember.
Yes.
But I can tell you the details now. It's very vague, for me.
Some more questions.
So what would be the next step toward proving the conjecture? Next large class.
Yeah, now we are working, as I said, now we are working on extending this for here, this theorem, we want to just remove this and work with polynomials which are linearly independent, but this is still very far. So this was really important, the fact that, we work with polynomials with distinct degrees, and now we want to understand, we want to match, to this. And that will be to this theorem of Franzikinatis and Kutza, where they have polynomials which are linearly independent. And that's, I think, this theorem is important because it closes some, some story, I would say, in the sense that, this, here we have class of polynomials which are linearly independent, and then, the complement will be polynomials which must be linearly dependent, and presumably the simplest class of this linearly dependent would be the situation where we have k equal 2 and here and two distinct transformations. That would be the first step to understand it, because Bourgain, you see, he understood the situation where we have single transformation k equal 2, and so the pointwise is known in this case. So now would be nice to understand okay, and now for linearly dependent, there are two ways, because first, to extend this to the trilinear situation, to just recover this situation of Furstenberg and Weiss, where we have trilinear operator along linear orbits, or the other important case would be to understand bilinear situation when we have two commuting transformations. These are two examples that definitely, when presumably the case of linearly independent polynomials will be understood, so presumably these two examples will be important to start to study the linearly dependent situation. So
it's much more complicated.
Yeah, it's much more complicated, and the fact comes from the fact that so I said that this set of integers, but I was unable to show this. The shift system is important because here you see that instead of studying this, we can immediately pass to the set of integers and study everything on the set of integers. And this is important from the pointwise convergence problem because first of all, the z or zk are abelian groups. And the Fourier transform is available. So the fact that we work with a group, it's a very, very important ingredient, here. And so, and here you see that these operators, even if we take a look at, so they are translation invariants. I mean, that if we put norm and we translate x by certain vector, then this does not affect the norm. But additionally, when here these polynomials here are linear, so then there are some another symmetries, modulation symmetries that we can modulate by multiplying by certain number from the unit circle, and this also does not affect the norm. And that's something, which does not arise, when we consider the case of, for instance, polynomials which are linearly independent or which have distinct degrees. But when we, drop this assumption about being linearly independent and we work with the case where they are linearly dependent, then there are some additional symmetries. And these symmetries cause some, they should, in fact, help us, to say something more, but in fact, they make the situation more difficult. And that's the problem. So therefore, this is now, it will be a different story. It's very tempting, but I know that there are people in harmonic analysis who spend, many years, trying, to understand, and they, at this moment, as far as I know, they went nowhere. So. Thank you.
More questions online, no more. Tea, coffee,